Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to go back to exoplanet detection again. I know I have lots of videos on this, but there's lots of different ways in which you can actually detect an exoplanet. And this one's a bit more of an exotic one. This is where we're trying to detect an exoplanet orbiting a pulsar. That's somewhat of a bit of a problem anyway, but I've done a separate video on how planets can actually get around pulsars in the first place, because these are essentially stars that have finished their life on the main sequence, very large stars, and the fact that planets are there is a little bit bizarre. How do they form? How do they get there? So I've done a separate video on that anyway. This one here is about how you actually detect them from the pulsars, basically from a pulsar. Now, before we do that, I basically want to recap what a pulsar is. Maybe you're not familiar with that. If you have, you can skip over to the final bit where we actually look at how we actually detect them around a pulsar. So pulsars are kind of like the end point of certain stars. So these are massive stars. They're not the most massive stars because they will then end up forming things like black holes, but these are stars that are more massive than the sun. And when they're on the main sequence, when they're basically a star, they're in hydrostatic equilibrium. That basically means that they're generating energy in their core and they're creating an outward radiative pressure which is balancing them against gravity. So they are in this equilibrium. And what happens actually is once they've used all their fuel up in their core, they then no longer produce that outward radiative pressure and they actually collapse. So here's the Crab Nebula, which actually has a pulsar at the center as well. So the fusion stops in the core, it collapses. It's only actually the central core which collapses to this like degenerate stellar remnant, which is a pulsar, neutron star. They're kind of the same sort of thing. Again, separate video on that. And then the outer layers are ejected in the form of a supernova, which is what we see here with the Crab Nebula. But the bit we're really interested in for this is the really dense pulsar at the center. So basically, as a general rule, pulsars are very fast rotators. They are fast spinning neutron stars and they can spin up to, hundreds of times a second. So these are very, very fast rotating. They are quite small. So generally, you can imagine them to be about the size of a city. So you're talking like 20 kilometer sort of size, very small, very dense, but also very heavy. So these are going to be heavier than the sun, but the size of a city. And then they actually have these polar jets that we see as a pulse. Now, those jets, these high energy jets, are not at the rotation axis. So they're not at the rotational poles. So we'll come back to that. But the reason why they spin so fast is that they are conserving angular momentum. So if the star was rotating, we know that the sun takes like approximately a month or so, it's actually less than a month, and it rotates at different speeds depending on the latitude. But it's rotating, and most stars are going to rotate. In fact, all stars are pretty much going to rotate. But if you collapse that, then to conserve angular momentum, it speeds up, and that's where the really fast rotation rates come from, is that conservation of angular momentum. Now, obviously, there's some ejection there and whatever, but as a general rule, that's why they're rotating really fast. So back to the actual, these jets, these beams that are coming out. So it's really fast rotating, but then you have these essentially these beams of radiation, very high radiation, which are not aligned to the rotation axis. So it's a bit like a lighthouse, really. These beams are sweeping out as it's rotating. And that's due to the fact that the magnetic axis is not aligned to the rotation axis. And these are the magnetic poles, not the rotational axis, essentially. So it depends on where the magnetic axis is in relation to the rotation axis. But what we see is these beams sweeping out in space, and if we're in the line of sight of that beam, we will see a pulse basically, and it might look like this. So on the y-axis you've got flux. That's essentially how bright the pulse is, the energy being emitted, and they're typically measured in the radio part of the spectrum, which is why it's noted as flux. And then on the x-axis is time. So if we're looking at a pulsar over time, it'll be quite quiet, and then we get a sudden spike in flux or energy being emitted from that. And obviously the time between each pulse is going to relate to the rotation period of that pulsar. And they can change They're different for each pulsar. There's a lot of complexity there, but we're not interested in that for this particular video. We just get a pulse per rotation of the pulsar. Now, pulsars are not particularly rare. There's over, or nearly 4,000 that have been discovered so far, and there's kind of a list here if you actually want to go check that out. So pulsars are not particularly rare, got lots of those. What is rare, however, is exoplanets or planets orbiting the pulsars. And as I mentioned before, the fact that they're there is unusual. Pulsars they form from massive stars. Massive stars struggle to form planets because they just have unstable kind of disks and things like that. So you don't typically find planets easily forming around massive stars. And even if you do, it has to go through the supernova. And any planets that are there, you would likely lose during that process. So planets that are orbiting pulsars quite likely formed after the star had already ended its main sequence life. But anyway, there's not many been found. And if you go on the Exoplanet archive and basically filter by pulsar, which I've done here, pulsar timing, which is what I'm going to show you how we actually discover those, there's only a handful basically. So they're quite rare. And actually, if you look really carefully, there's one system there that's got 3. So 3 of those planets are actually around a single pulsar. That's actually quite interesting in itself. So basically, if we do have a planet and a pulsar system, they orbit a common center of mass, the barycenter. So the planet doesn't orbit the pulsar, they orbit a common center of mass, but because the pulsar is so much more massive than the planet, it kind of wobbles a little bit, a bit like the radial velocity method that we detect planets with around stars anyway. So the pulsar kind of does a little orbit here, while the actual main planet is on a bigger orbit, but they're orbiting a common center of mass, the barycenter. Now, what happens then, if we're observing a pulsar, the distance between that pulsar is changing. And that means that the pulse we measure appears earlier or later than it should do. So we get a kind of like a delay, or it appears early because the distance between us and the pulsar is changing because of this orbit around the barycenter. And that pulse then either kind of moves closer in time or further away. So again, we get a late or early pulse if we're measuring it. So we're measuring it over time. And then what we want to do actually is measure the time between each pulse when it should occur. We know when it should because actually they're pretty good clocks, basically, pulsars. So the time between each pulse is pretty stable. So yeah, stable is probably the right way of saying that. So when that changes, we can measure that. We can measure if it's been early or late, and then we can create a plot of that. And interestingly, what happens here, if we were to measure the variation in the time arrival of that pulse, we will get something that might look a bit like a sine wave, a bit like this here. So it will actually get earlier and then later. And along the x-axis there is time, but it's put in terms of orbital phase here. So that's one orbital phase of the system. That's not the rotation of the pulsar. That's due to the orbit of the planet and the pulsar around the barycenter. So we can get the orbital period of the exoplanet and also the pulsar by looking at this changing timing variation of the pulsars of when they arrive, if they get early or late, basically. So yeah, so basically if we can get that nice sine wave there, we've got the orbital period of the planet. And also the amplitude of that timing variation can also give us kind of the masses as well, because we'd expect the distances to change more if you had a bigger planet and a smaller pulsar. We can measure the mass of the pulsar maybe in a different way. Mass of the actual exoplanet we can get by looking at this in the same sort of manner in which we might do a radial velocity. A bigger planet causes a bigger wobble of the star. Same with a pulsar. Now, I mentioned before from the Exoplanet archive, one that had 3 planets. Now, this one here has 3 kind of terrestrial planets, and they range from about 2% the mass of the Earth, which is a pretty small planet, if I'm being honest, up to just over, well, not just over, but about 4 1/3 times the mass of Earth. So there's 3 planets there that are likely going to be rocky terrestrial planets. And this is around a fairly old, so it's about 10 to the 9 gig years or sorry, yeah, I should say that's in gig years, and it's a millisecond pulsar basically. But I'll leave that for you to kind of look at what they are in more detail. But this one in particular is quite interesting because why have we got three? And the fact that they've got planets is even more intriguing because it's quite complex for a pulsar to get a planet. Now, thank you for watching, and if you enjoy the videos or you do find them helpful, then do consider becoming a member of the channel. I put extra videos in the member section, there's other benefits, and it also just generally helps support the channel as well. So thank you for watching.